My name is Avery Thomas, and this is my 5th lab for Physics 2211. For this lab, I've decided to analyze what it would be like to build my own indoor skydiving wind tunnel. Throughout this process, I will be explaining some fundamental physics principles like gravity, drag, and terminal velocity. The goal of this lab is to determine who will have the highest terminal velocity out of 3 people with various masses, therefore determining the relationship between mass and terminal velocity. This is important because gravity affects everybody on this planet, and we should understand how this affects our motion. I will accomplish this in 2 steps. I will first do this by deriving the terminal velocity formula from our known forces acting on the person in the wind tunnel and calculating this value for each of the 3 people. Following this, I will verify my answer by creating a computational model of what the 3 people would look like in the wind tunnel and observing who had the highest terminal velocity. Both of these steps will be done in GlowScript. At the end, I found that the higher your mass, the higher your velocity will be. First, I want to explain what is involved in regular skydiving, which most of us are probably already familiar with. I included a little video clip just in case, and I'll play this now. Basically, you start from a position of rest in a helicopter and then jump. At this point, the gravitational force will pull you down, and you will accelerate according to the acceleration constant of 9.8 meters per second squared until you reach terminal velocity. This is the point where the gravitational force acting on you equals the drag or wind resistance pushing against you, so that there is no net force and you are moving at a constant velocity. When comparing regular skydiving and indoor skydiving, most of the physics principles at work stay the same. In this case, though, you begin on the ground in a wind tunnel. The fans underneath of you will turn on, and what we will call the wind force begins to act on you, pushing you up. Once the wind force and the gravitational force equal each other, there will be no net force acting on you, and you will have reached terminal velocity. In this case, you will remain at rest in the air, essentially floating. To begin, I first had to figure out how to calculate terminal velocity using the forces we know are acting on a person in the tunnel, gravity and the wind force. We know that gravity equals mass times the acceleration constant of 9.8 and is negative because it acts in the negative y direction. We also know that the wind force or drag force will equal the drag coefficient times the air density, which is represented by p, times velocity squared, times the surface area of the cross-section of the falling object, represented by a, all divided by 2. If you know that the wind force minus gravity equals 0, then we can work out our equation so that terminal velocity equals the square root of 2 times the gravitational force, which is mass, times little g, all over the drag coefficient times p times a. The next thing I had to consider was how I wanted to computationally model my terminal velocities. I set up my wind tunnel in GlowScript and set my tunnel to be 4 meters in length and 5 meters tall. You will see this later once I run my code. I then began coding. I chose the 3 people in my wind tunnel to have the masses of 60 kilograms, 70 kilograms, and 80 kilograms because the average human has a mass of 70 kilograms and I wanted to have one slightly above and slightly below this average. I then placed my people within the wind tunnel, each 1 meter apart from each other so that they could easily be compared. They all began from a position of rest because I'm essentially modeling what would happen if the person was standing and the wind tunnel just turned on. Time began at 0 and I input the rest of my initial conditions and given variables. Little g is 9.8, p equaled 1.225 for the air density in our atmosphere, A equaled 0.75, which is the average cross-section of a person, falling with their arms and legs stretched out, and the coefficient of drag equaled 0.7, and the wind force began at 0 because it was initially turned off. I calculated the gravitational force and the terminal velocity for each of the 3 people. I then created my calculation loop so that while the gravitational force did not equal the wind force, and therefore the net force was not 0, the wind would increase and the velocity of the person would change along with her position. Then time would increase and the loop would run again until the gravitational force equaled the wind force and the net force was 0, meaning that the person had reached terminal velocity. I did this loop for each of the 3 people, but only show it here for the first person because it was the same code, just with different variable names. This then created the model that I will play now. As you can see, the 3rd person represented by the yellow ball rose the highest and therefore took longer to reach terminal velocity and had the highest terminal velocity. The 2nd person was next and the 1st person had the lowest terminal velocity. This was also reflected by my calculations and you can see this on the left, where person 1 had the lowest terminal velocity of 42.7618 and person 3 had the highest at 49.3771, with person 2 in the middle with 46.188. Overall, this lab was only accomplished because I assumed a lot of potential variables, such as the air density and the person's cross-section surface area, which would really likely change with every different body position as the wind tunnel turned on. Also, it is likely that with higher mass, you would have a larger cross-section area. However, I did not include these, and therefore this limits how realistic my model is. In the future, I would fix these, and I would also be curious to determine the body position that makes you reach terminal velocity the fastest. Thank you.